Hello! Today we're going to be talking about the sequence architecture, which is a messaging middleware solution widely used in the financial industry. Some of the top market makers, exchanges, prop trading firms, and banks use the sequencer to implement their trading systems. As you'll see throughout this presentation, it allows you to create a deterministic distributed system that takes care of every real-time aspect of your company. So without further ado, let's start. So that's our main agenda for today. You can pause the video to check the topics we're going to be talking. As for the history of the sequencer, we know it was born on Island ECN back in the 90s. A lot of smart people have worked at Island, and today they are known as Island alumni. Then Island was bought by Insnet, which was later bought by Nasdaq, which uses the sequence architecture to this day. Many of the former Island employees went to financial firms in Wall Street to implement their trading platforms using the sequence architecture. Brian Nigito, who is the former CTO of Island, has a popular YouTube video where he describes the sequence architecture in the context of an exchange. We highly recommend that you watch this video too. The sequence architecture is still used today by the largest and most successful market makers. These companies are placing millions of orders daily in a variety of markets and care deeply about latency. In other words, every microsecond counts, and performance can be the difference between a successful trade and a trade that loses money. So now we'll be talking about the main characteristics of the sequencer architecture. By far, the most important characteristic is that all nodes read all messages in the exact same order always. That's responsible to giving the deterministic factor for this architecture. There is no inconsistency across nodes because every node is going to read exactly the same thing, the same event stream, the same topic. There is no such thing as two topics in parallel. Every node gets all the messages in the exact same order, and that's going to give you consistency because everybody sees the same thing. That there cannot be any kind of mismatch between two nodes because one node saw something and another node saw something else. It allows the nodes to become deterministic finite-state machines, meaning same input will always generate the same output. So this is a single topic. The messages are total ordered. Nodes can quickly drop message they are not interested in. So if I'm a node that I'm only interested in a certain message type, I'll just read the whole event stream and quickly drop message that I'm not interested in. As you see, this system is very, very fast, so it's not a problem for a node to skip the message it's not interested in. So all messages are persisted, and a late joining node can rewind to rebuild the exact same state it had before. So if that allows you to have like clusters. If a node is joining late into the session, it will get all the message that it missed from sequence number 1 and rebuild the same state as a node that's live and running. So that allows you to bring extra nodes up and down in a cluster. So let's say you have like a backup sequencer that's running. There's a problem with that machine. You need to put it someplace else. Simply bring up a new machine, launch the backup sequence there. It will quickly catch up, rewind from sequence number 1. So it will rebuild the exact same state as the live sequencer has. So it joins the cluster and becomes like a mirror. So those, like I said, those become deterministic finite state machines. That's very important. Even the clock is deterministic, because if each machine is using its own clock, then the system is not going to be deterministic. So the way that works is there's like a centralized system clock that every machine uses, and this clock ticks on the event stream itself. So every machine has the same clock. So when a machine timestamps a message with, for example, an execution time, the other machine is going to use the exact same timestamp to create the exact same state. And like I'm saying here, that allows you to have highly available dynamic clusters. That becomes natural and trivial because now both nodes in a cluster, they are seeing the exact same input, they are running the exact same code, even the clock is the same, so mathematically they're going to create the exact same state. Message distribution is done for a reliable multicast UDP protocol. That's very important because multicasts allow you to push the problem of distributing message to the hardware, to the switch, to the network switch. So the sequence sends the message once, and the underlying hardware architecture, network architecture, takes care of like distributing the message in a fair way and in the fastest way. And that's what multicast UDP gives you. So as you'll be seeing, we use the mode UDP protocol to implement a reliable multicast UDP protocol that doesn't lose messages. We'll be talking about that later. No message is ever lost. Like I said, all nodes have to receive all the messages, always. That's a premise of this system. And each session is automatically archived with all its messages, so it can be replayed anytime in the future. So every trading day, or every session as we call, is archived, and then later you can use it to simulation, auditing, testing, reports, debugging. It becomes like the DNA of what happened on that day in your firm. So 2 years from now, if you want to refer back of what exactly happened on your company on that day, you take the session file, and everything, all the messages are there, and you can replay those messages to reproduce, investigate, report exactly what happened on that session, on that day. So CoralSequencer is an implementation done by us here at Coral Blocks of the sequence architecture. It's been around for 9 years since we first started, and right now we can say it's full-fledged, feature-rich, bug-free, because it's been in production for a long time and we seldom receive like bug reports from our customers. So it's in a very stable position right now in terms of production quality. We are always evolving from feedback from our clients. I mean, this product has been stressed from multiple angles, from exchanges, banks, on the buy side, sell side. So from this feedback of real case scenarios in production, we've been evolving with new features, bug fixes, of course. So yeah, it's in a very good, stable position as we speak. CoralSequencer is used as the backbone of an extensive project from a major tier 1 US investment bank that completely revamped their entire trading platform. And it is today used by countless teams globally with outstanding results. We like to mention this particular case among all our clients' success stories to showcase how much the code base is battle tested in production. And because we know that complex low latency infrastructure software takes time to mature and evolve. And that maturity can only come from real case scenarios in production. There are no shortcuts for a system to mature, and we feel that we have reached that point, so we can say that CoralSequencer is production ready and battle tested. CoralSequencer is built with ultra low latency in mind, because the companies that are going to be using the system really care about latency. We favor latency over throughput, but that doesn't mean the throughput is low. So to give you an idea, the current record on a very fast machine was 2.7 micros. The average was about like 4 microseconds. So this time was like the very minimum time of the fastest round trip message that was sent on the system, on the network. We like to tell our customers that, of course, it depends on their hardware, it depends on their network infrastructure, but our goal here is to keep the average time at single-digit microsecond. Ideally on like around 5 or 6 microsecond per round trip. So that includes like putting a message on the event stream and seeing the message back on the bus. So in terms of throughput, that depends on how much batching you are able to get, because of course a UDP packet has 1500 bytes. If you can put more than one message on the same packet, the message gets a free ride. So the throughput, if you do a lot of batching, the throughput can go as high as 2 million messages per second. One of the most important characteristics of CoralSequence, which I believe is kind of like a requirement for any system that wants to be a sequencer, is the fact that it's single-threaded and uses non-blocking network I/O. By non-blocking network I/O, I'm talking about selectors, non-blocking sockets. We use Linux ePAL, which is very, very fast. Our Linux ePAL does not create any garbage. It's completely garbage free. And the thing about single thread is not only performance, it's gonna give you very, very high performance because the thread's gonna be pinned to an isolated CPU core, spinning and receiving message from the client. But I'm talking about it frees yourself from the multi-threading bugs and pitfalls. Suddenly you don't have to worry about race conditions, synchronization, locks, deadlocks, and things like that. Everything is single-threaded, even if you have like 3, 4, 5 different clients and servers running at the same time, they all gonna be executed by the same selector. So this is completely single-threaded. Yeah, it's also important for determinism, right? Because if you have multiple threads, kind of like loses determinism because you never know the order the threads are gonna execute. So single-threaded and non-blocking, it's very convenient. It makes like programming joyful and it gives you like a very high performance. So what else? A zero garbage created per message. Our ePAL implementation is zero garbage. So you can send millions, billions of messages without ever creating a single drop of garbage. That means no GC overhead. We use Java as a syntax language. We do a lot of object pooling. So we never like releasing trash to the GC. The sys has no single point of failure. Everything has a redundancy node. Like I was talking in the beginning, this system allows cluster in a very natural way. So it's possible to have a cluster for every node, for every actor of the system. And at the hardware level, you also want to have redundancy, right? For example, you don't want to have the backup sequencer connected to the same switch of the main sequencer, because if the network switch breaks, then you are in trouble. So you want to like distribute the actors and the cluster across redundant hardware. So if one hardware breaks, system can still continue without that hardware. Exchanges will do that across data centers. So we would have like a sequencer in one data center, a backup sequencer running in another data center. So if the whole data center goes off, you still can fall over to the other data center. And this system is message agnostic, meaning like CoralSequence was done to transport any kind of message you want. You can use any like format you want for those messages. You can use flat buffers, SBE. You can use your own serialization framework that you build in-house. You can use our Coral Proto, which is available on our GitHub. It's up to you to decide what kind of serialization framework you want to use. And last but not least, the system has a very high level API, meaning like sequencer is a very complex system, a very complex architecture. I mean, it's not difficult to understand, but it's very difficult to implement. So the high level API protects you from all this complexity. You don't need to know it all to use it. You can take a new hire that never seen the sequencer before. In half a day, you tell him how the basics work, and he's coding a node to do whatever you want. So yeah, that's pretty much what sets CoralSequencer apart. like I said, we are always evolving, and later on we're going to be seeing a demo using CoralSequencer. So now let's talk about some diagrams of the sequence architecture. In the center, as like the main broker, the centralized broker is the sequencer, which is going to be receiving all the messages, timestamping and sequencing every message and putting the messages on the event stream. So the sequence is the single source of truth, meaning like it has the power to decide how the messages are going to show up in the event stream. So it has like a single incoming UDP channel receiving messages. So it's a single line for all nodes. Nodes have to compete for a position on that queue. I mean, later we're gonna know how we implement fairness on the system, so no node can flood and take control of the incoming channel. We'll talk about that later. So the sequencer is getting the messages and putting the message on the event stream. So we have replayers. We can have a cluster of replayers around the sequencer. The replayers are the ones responsible for two very important things. One thing is gap filling, meaning when there is a gap in the line, meaning when there is a packet loss, the replayer is going to retransmit that packet to the node that lost it. And the replayers also take care of rewinding. That's when like a late joining node joins into the session and it needs to get all the message from sequence 1. That's how the clusters are implemented. For example, if you want to bring a replayer in the middle of the day, how does it know about all the messages that already happened? It's going to rewind for another replayer and rebuild the exact same state to join the session, to join the cluster of replayers. The backup sequencer works the same way. You can bring as many backup sequences as you want anytime during the session. They can join late. For example, if you have a backup sequence in a machine and you want to move it to another machine, simply bring it down, bring it up in another machine, and it's going to rewind from a replayer, rebuild the same state, and be ready to join the cluster, to join the session. Then you have archiver, which is very important. It's the node responsible for saving the whole event stream to a binary file for later reference. So later you can replay that file, use the file for backtesting, debugging, whatever you want. We're going to be seeing an example of that when you see the demo with CoralSequencer later. Then you have the logger, which is kind of like the archiver, but it logs to a file in ASCII. That's pretty much for a human to look and see. The binary file won't see anything because everything is binary, but the logger, you'll be able to see the messages in ASCII. You have the bridge, which allows other nodes to connect through TCP if they want to. And it gives some kind of like a middleman between the sequencer and, for example, slow nodes or nodes that are on another network across the globe, on another data center. They can connect through the bridge. They rewind from the bridge. They're using TCP, so packet losses, it doesn't happen. What can happen, of course, is disconnect. And there's a protocol, a TCP protocol that takes care of that, like we're going to be seeing later on. So I'm not going to spend time talking about that now. And then lastly, the dispatcher. The dispatcher takes care of like share memory. So let's say you have like 20 nodes in a single machine. You don't want to have 20 nodes like listening on the network card for 20 streams. So what happens is instead of having 20 nodes listening to your network card, you have a single node called the dispatcher. The dispatcher reads the message, put on a shared memory on the same machine, and all the nodes on that machine read those messages for shared memory. That speeds up things a lot because when you have like, especially when you're using kernel bypass, which it makes it hard to have like many like multicast listens on the same machine, because now the buffers is not on the kernel, it's on the network card itself. And of course the amount of memory on the network card is limited. So having like a single multicast channel, single multicast listener on the machine, writing to share memory, and then all other nodes, 20, 30, 100 nodes on the machine if you want to, they're all gonna read from the same share memory. So yeah, the dispatcher is very cool. So to make it easy to see the diagram, let's just like combine all the actors of the sequencer in a small circle. Just put like the first letter for each actor, and then we make it smaller so you can understand that's the whole sequencer. And then around the sequencer, we have the nodes. The nodes are the applications that are sending messages and receiving messages from the sequencer. And like I said before, they all receive the exact same message in the exact same order. Now we're going to be talking about the two protocols that the sequencer use to implement reliability. The most important one, of course, is for reliable multicast UDP. Of course, packets sent by UDP can get lost, so we need a reliable UDP protocol to recover those lost packets. And mode UDP is the protocol that has been historically used by the sequencer architecture. It's as old as the sequencer itself. It's to this day used by NASDAQ for its each market data feed. And the other one is sub-bean TCP, which is to implement reliability on top of TCP, which is kind of like, what? TCP is not reliable? I thought it was. Anyway, the next slide is going to answer that question. But those two protocols are kind of like paramount for the sequence architecture because they allow all the message to flow no matter what happens to the network. If there is a packet drop, if there is a TCP disconnect, no matter what happens, the messages are going to get to the other side. So let's talk about why TCP is unreliable. The short answer is when there is like a disconnect, any message in the underlying socket buffers are going to be lost. And the longer answer is TCP only guarantees reliability for the TCP frames from TCP stack to TCP stack, not from application to application. Like I said before, any message sitting on the underlying socket buffer on either side, on the send buffer or receive buffer, if there is a TCP connection break or disconnect, those messages are lost and need to be retransmitted once the connection is reestablished. So now we're going to move to the fun part, which is going to be a demo of the sequence architecture through CoralSequencer. We are going to be showing a simple OMS, of course, like a proof of concept one. We have like 5 different message types here to place orders and receive cancellations and executions. We have an order port, placing orders. We have a gateway picking up those messages and pretending it's sending to an exchange. For simplicity here, we're just going to execute the orders that have like an odd client order ID, and the orders that have an even client order ID, they're just going to sit on the book doing nothing. And the position one is going to go into the sequencer, listen to the event stream, and track the position. So it's going to know how many shares of IBM do I have, or Apple. So by watching the sequencer, it's able to easily calculate this information. And note that the position monitor is like a read-only node. It doesn't place any messages on the sequencer. It just listens to the sequencer event stream. The order port is going to place messages, those messages, the new order and the cancel order, and the gateway is going to send the message, order accepted, order cancel, and order executed. So let's jump right into the terminal to see this in practice. So I have 2 machines here. One is called Cleveland, the other one is called New York. I'm going to be running everything inside Cleveland. I'm just going to be using New York when I test the player. So let's start the sequence on the Cleveland machine. Okay, sequence started. It logs a bunch of things. I'm going to make this window bigger so you can see the logs. Basically, the sequence is running. Let's start the player. And again, everything is running on the same machine. You can run the whole sequence architecture on a single machine. No problem at all. So now the replayer is running. You can see connected to the sequencer to rewind. It got all the message from the sequencer and now it's running. So here are the logs of the replayer. As you can see, send the replay request to the sequencer, got the messages it missed, and now it's ready to rumble. Now I'm going to start an archiver. Like I said, our archiver is going to save all the message to a binary file. Later I can use that file to debug and do whatever I want. You'll see an example of that. Now I'm going to start the sprite, which is a protocol that connects to the replayer and get all the messages from the replayer itself. So as you can see, there's 3 messages already in the sequencer. Those are internal messages. Those are messages belonging to the CoralSequencer. So those are in blue. The application messages are going to be in white, as you see. Now I'm going to start the which one? The order port. Let's start the order port. Order port's running. I'm going to start the position monitor. Position monitor is running. And now I'm going to start the gateway. Let's start the gateway. The gateway, it's running. Notice that's connecting to the replayer to rewind. Now I'm going to telnet to the order port. That's an easy way to control the node. As you can see, it accepted a telnet admin connection. So I'm connected. You can list. See, they have like the OP01, order port 01, has a bunch of admin commands that I can execute, and has this command called send command, which is you can use to send a message to the sequencer. So I send the message hello. As you can see, the message it's on the event stream now. You see the message there, and I can send another message. And notice that the message has sequence 6. It's going to the event stream. The sequence is pushing the message to the event stream. All nodes are receiving these messages. Now I'm going to start the logger node. I'm using the sprite, but you can also use the logger. The logger is going to log everything to a file. So let me get out of the sprite here and open this file, which is the logger file. And let's see what it is. It's inside the logger log1 folder. IVI this file, as you can see, the messages are there. And you can also tail, and that goes to a file. You can keep the file, you can see the file later. I like to use the sprite because the sprite has colors and it doesn't go to a file, it goes straight to the terminal. So I send another message, hello yet again. And an interesting thing here is you can kill the logger and restart, and all the messages are going to show up. How is that possible? For example, if I come here while the logger is dead, if I come here and send another message, it went to the event stream. I don't see it, but let's start the logger again. So I start the logger again. I go to the file, and yes, the message is there. How did that happen? Of course, it's rewinding. So whenever you restart the logger, it connects to the replayer, rewinds from sequence number 1, and gets all the messages. You can even delete the file, the logger file, and then you run the logger again, recreates the file, recreates all the message. Again, it's rewinding from the replayer. A late joining node gets all the message from sequence 1. That's how the deterministic behavior it's accomplished, and the clusters are possible. We'll see that later. So okay, so I'm gonna use the sprite connecting straight to the replayer, because it has colors and it doesn't go to a file. I don't need to tail the file. It goes to the terminal. So yeah, I like that. So okay, so let's what do we do now? We should telnet to the position monitor. Okay, there's a admin port, which for this guy is 50,053. We're connected. Again, we can list. You see the account for this node is PM01, and it has some admin commands, and it has a interesting admin commands called drop packets. That's useful to test like the replayer and the gap filling, meaning like how reliable is this really. We'll see now. So I told the node to drop the next packet. I'm gonna send a message, hi again. I send a message. Look what happened. The node is saying like, whoa, I got like a gap fill. I'm gonna send a replay request. The replayer got a replay request, and the replayer retransmitted the lost message to the node. You can see that it sent a replay request, and it got the message that it lost. And the interesting thing here is the first time it sends a replay request, it sends to the multicast channel. That's called multicast discovery. And then all replayers are going to reply. The first one that replies, it assumes this one as its chosen replayer. So we records its IP address, and from now on it's going to unicast to every player and instead of multicasting. So let's continue here and telnet to the admin port of the gateway. We are there. Gateway, it's there. We list the admin commands of the gateway. You see you have list orders. And if we list the positions here of the position manager, you see 0 positions. But let's first go to the order port. Let's place an order here. So I'm gonna place an order for Apple. Let's say IBM, and it's gonna be a buy order, true, and the quantity is gonna be 500, and the price is gonna be 45.44 cents, and the client order ID is gonna be 321. So IBM buy 500 size, 45.45 price, and client order ID 321. Because the client order ID was a odd number, 321, the gateway immediately executes it. So now my position has changed. Now I have 500 shares of IBM because my order was just executed. You can see here that the gateway is executing the order. First it accepts the order, sends the order accepted, and then it sends the order executed. If you see up there on the sprite, you see those orders flowing on the event stream. So now I can list the orders on the order port. No orders because the order was executed, so I don't have any open orders. I can list my positions, and of course my position is 500 shares of IBM because I just bought 500 shares. My order was executed. And if I list the orders on my gateway, of course I have no open orders. Oops, what happens here? Oh, I typed the account name incorrectly. It's GW instead of GM. Great. So, okay. The orders for the gateway, no orders because there's no open orders. Now let's place an order with even client order ID so it doesn't get executed. So now you see the gateway send the order accepted but it never executed. The order is now sitting on the book. If you list the orders of the gateway, you see the open order. If you list the orders on the order port, you're gonna see 2. But let's place another order now, different price, another even number, so doesn't get executed. So now I have 2 open orders on the gateway and 2, of course, open orders on the order port. They have to match, of course. So now, what else should I see here? Oh, I just queued the gateway. I just queued the order port. Oh my god, what happens now? I just queued my order port. Let's restart it. I restart the order port. It rewinds. Guess what? It just created the exact same state that it had before. So if I list my orders, the orders are there. Like I said, finite-state machine, same input, same output, same state was created. And as you can see, as it was rewinding, it was getting all the past message and rebuilding state, accepting, and everything. So that's the beauty of deterministic finite-state machines. So let's place another order. Now I'm gonna sell, so my position decreases. I'm gonna sell like 100 shares. I'm gonna put an odd number so it gets executed by the gateway immediately. Let's send that, and then what happens? When I send, it gets executed. You see the order execution message was placed. If you see all the way up there, you see on the sprite the orders are flowing, and now my position, of course, decreased by 100. I only have 400 shares of IBM now because I just sold 100 shares. So that's like a simple OMS like running here. But the beautiful thing is, if I now come here and kill the position monitor, oh my god, what happens now? I lost everything. I don't know my position. No, just restart it. It rebuild state. And now if you list the position is there. So that gives you like a cluster. You can have like a second one running. If you can pull the plug of this one, and the other one is going to still be there doing the exact same state. Same thing for the gateway. I can kill the gateway like I'm doing here now. Oh my god, the gateway is dead. Start the gateway. It rebuilds state from the event stream for rewinding, and now I still have my orders there. So we rebuild the book, the open orders that I had in my book. So I never lose my state. You can have like 2 gateways running in parallel in a cluster. If one fails, you have the other one. You can pull the plug of the machine and everything works. That's called like a hot cluster or a hot failover. So now I'm going to be showing you multicast discovery, which is a very cool feature of CoralSequencer. So I'm going to start a second replayer on the New York machine, a different machine. It's going to join the cluster. Now I have a cluster of replayers. I effectively have two replayers running in a cluster, one in the Cleveland machine and the second one on the New York machine. So when I come here to the position monitor, and let's see what I'm gonna do with this position monitor. Let me queue it, and let me also queue the first replayer. So now I only have the second replayer, and let me restart the position monitor. When I restart the position monitor, it's gonna send a multicast request to all replayers on the entire network. They're all gonna reply. It's gonna choose the one that arrives first because it's gonna assume it's the one closest to it, and then if now I drop a packet, it's also gonna choose a replayer for gap filling. So it chooses a replayer twice. First it chooses a replayer for rewinding, then it chooses a replayer for gap filling. That's gonna happen here now. When I send a packet, that's gonna send a replay request to the multicast address. I only have one replayer, so that's the only replayer that's gonna reply. As you can see, that's gonna be my chosen replayer, the only one that replied. If you come back here, very important to notice that the destination of my replay request was the multicast address. That's the multicast discovery happening. I don't know where the replayer is, so I have to send it the multicast address. Once I get a response, then I choose my replayer. So now I chose this replayer here, and the next time I have like a gap, I'm gonna send a message to that replayer because I already chose it. So now let's kill the replayer I just chosen. Now I chose a replayer that's not there anymore. Oh my god, what's gonna happen? Now I'm gonna have another packet drop. Let's send a message that's gonna be dropped, and then what happens? Oh my god, I saw some like pink message there. Let's see what happened here. I was unicasting a replay request to a replayer that was not there anymore, so I got like a gap fill timeout. When that happens, eventually I assume the replayer is dead, and I switch back from unicast to multicast. So the cycle repeats. I go to multicast again, and I choose another replayer. So see, I chose a different IP address now. I just found a different replayer in a different IP address. So now let's talk about message fragmentation. I'm gonna send a big message now so you can see how CoralSequencer breaks the message using its underlying protocol. As you know, a UDP packet has only 1500 bytes. That's the MTU, the maximum transmission unit. So now if I go and send like a very big message, send large command. So I'm gonna send hello friend, how many times? To go above 1500. Let's send 400 times. That should be enough. 300 should be enough. So when I send a big message, let's see the message flowing. See, the message is huge. So it actually took me like 3 packets, 3 internal messages. That's why they're showing in blue to send my big message. So CoralSequencer automatically breaks the message in parts and send it through the wire in 3 UDP packets. And then on this other side, it will reassemble the message and give the message transparently to the application. You don't even need to know that that's happening on the hood. Now if I send like a small message again, it sends just the message as an application message. So that's very, very convenient because it allows you to send any message size you want. Now let's talk about the archiver. The archiver is saving all the event stream to a binary file. Let's queue it. No problem, you can always restart it again, remember, but let's see the files that it has generated. Let's go into the folder of the archiver. So it generated this file here with 27 messages. It's I call like a store session file. So let's get that file. Let's go to the order port, and let me VI the MQ file. The MQ file is the file that we use to start a node. It has a very simple DSL. You see. So I already have here one that's passing the load from URL. That's the URL from the file, the local file that I'm gonna be loading to reprocess all the message. When I do that, I'm gonna do this completely offline. I don't even need the internet. So I just run it. It read the file. It executed all the messages. See the file that he read, the file that the archiver has generated. And like I said, I didn't talk to the sequence. I didn't talk to the network. I just reprocessed the file from my local file system. I can do the same thing with the position monitor. Let's VI that guy. Position monitor file. Again, I already added the load from URL. The file is there. Let's run that guy again. So position monitor file, and it process again. It's doing that offline. It's not talking to the sequencer. It's just taking the message from a file and reprocessing them for debugging. So now let's talk about rewinding straight from a local file. Most of the time you're going to have a replayer running on the same local machine that the nodes are running. So why not just read the file instead of going through the network? That can speed the rewinding process like threefold. So here, as you can see, I'm specifying the directory where the replayer file is, and I'm suggesting a rewinder on the local host. So now when I execute this, my node with this configuration, POC WT or the port local replayer, it rewinds, but it's rewinding from the file. If you check the logs, where is it? You see that it found the file. Where is it? Somewhere in here. Oh, right here, about to start reading from the store file. So it just opened the file and read it. That's like at least 3 times faster than going through the network and open a TCP connection and reading the file. So when you have like a file with millions of messages, that can save you a big chunk of time. So now we're going to be seeing how we can change the transport protocol from UDP to TCP without changing a single line of code. This is all done for configuration. So let me kill everything. I'm killing everything here. Let me VI into the sequencer when it's configured to run on TCP mode. For example, if you're running on the cloud, you're probably not going to have multicast UDP there, so you want to use TCP instead. So all you have to do is put protocol equal TCP on the sequencer MQ file. And that's it. Now you start the sequencer, it's going to come up in TCP mode. It's going to expect TCP connections instead of multicast. So it's running, same thing with the replayer. I'm going to change my replayer to TCP mode, but first let's see that it's using actually a short payload TCP server and a soup bean publisher. Do you remember the soup bean protocol we were talking about for TCP? That's the protocol you're going to be using. So let's take the replayer now and change it to TCP. I already have an MQ file here. I already did that change, and you can see it there. All I have to do is specify the sequencer IP address. And remember, there's no multicast discovery for TCP. There's no such thing as multicast TCP, so I have to specify the IP address that I want to connect. So let's start the replayer now. It's gonna connect to the sequencer that I told it to. It has a soup bean client because it's connected to the soup bean publisher. And okay, I have a sequencer, I have a replayer in TCP. Now I'm gonna connect my nodes in TCP. I already have the MQ file for those nodes. I'm just gonna show you so you can see how easy it is to make it change to TCP. Again, there's not a single line of code change here. It's all configuration. You can change from UDP to TCP through a flag flip. It's that easy. So okay, I have my other port now running in TCP mode. It's connecting to the sequencer through the Supin client. I do the same thing for the position monitor. I already have one. It's gonna connect to the replayer through TCP, rewind, then connect to the sequence through TCP. Same thing for the gateway, TCP mode. Everything is TCP now. There's not a single UDP packet flowing here. So now let's talk about some interesting and advanced features of CoralSequencer. Again, not every sequence architecture is going to have those features, but they're very cool. So the first one is that nodes can commit a sequence number so that they don't need to reprocess the whole event stream and rewinding. Let's imagine you have a node that's inserted into a database, every single message. If it gets restarted, you don't need to receive all the message that you have already inserted in the database. So as you insert the message to the database, you can commit the sequence that you have already inserted in the database. So if you get restarted, it's gonna know that, okay, I already processed like those million messages. Please give me the event stream from that sequence on. I don't need to get everything. That's of course a special condition. The node doesn't care at all about determinism. It's not gonna be rebuilding state. It just needs to restart where it left off. So committing a sequence in this situation can be a good thing to avoid having to reprocess the whole event stream for nothing. Another interesting feature is that nodes can choose from which sequence number to rewind, allowing for managing state in customer snapshot servers. So some companies, they want to have like a very, very, very long session. So it becomes like impractical to rewind from sequence 1. It's gonna start to take like a long time. So one solution for that is to have like some snapshot servers. So what happens is every now and then you take a snapshot of your state, save in a server, so you know like, okay, until sequence 1,300,000 I'm at that state. So when you restart, you take the snapshot from the server and then you rewind only from sequence number 1,300,000. So then you can reapply the changes, the incremental changes from the last snapshot you took and not from the beginning. So that's another advanced feature. I mean, usually prefer to rewind from 1, not to break again the determinism. But if you wanna have a snapshot server, so you can take periodic snapshots and rewind from the last sequence from your last snapshot, you can. We haven't talked too much about bridges, but they are very powerful and very flexible. One thing you can do is have like a long distance bridge that use 2 redundant channels, one with TCP and one with UDP. So you send the message on both channels and whatever gets there first is the message that's used. So of course UDP can get lost, especially over long distance, but you can send both and kind of like arbitrate between those channels and get whatever packet arrives first. People used to do that with microwave antennas to connect New York to Chicago. Basically, you would send the packet through the microwave and the packet through the physical line. Whatever packet gets there first, you would take it. Microwave was kind of unreliable when they had bad weather, so that was a good strategy to make sure the packet always gets to the other side. Another very cool feature of the sequencer is its ability to batch aggressively. I mean, that's built on the mode protocol itself. The mode protocol itself supports batching. So the sequence is receiving a lot of message from a lot of nodes. It will just like batch as much as possible inside the same UDP packet. So that's done automatically. It reads as much as it can. I mean, of course, it reads a certain read buffer that's also defined, but has like a, I think like a 16K size. I don't remember exactly the size, but so it reads a batch from the network and aggressively batches the messages. So it tries to put as many messages as possible inside the same UDP packet. So by aggressively batching, it can increase throughput a lot. It can also increase latency because now a message gets a free ride, doesn't have to wait, can get the same ride, the same packet as the previous message. So yeah, it's a very important thing that the sequencer does. You don't have to do anything about it. It works out of the box. It automatically and transparently and aggressively batches the message it's sending out. Another very important feature is the ability for nodes to send in-flight messages to the sequencer. Instead of having to send a message, wait for an ACK, and then send the next message, wait for an ACK, it can send like a batch of messages before it gets the ACK. But that creates a problem. We don't want to allow any node to flood the sequencer with its own messages. That would compromise the fairness of the system. So that's, by default, the number of messages that the node can send in flight to the sequencer is 32. If it sends more than 32, it's going to wait for some X from the sequencer to arrive, and then you send more messages. That number is configurable, so you might want to have like a node or some other node that gets more priority into the sequencer. And when I mean by priority, I mean like the ability to place your messages on the unique single sequencer incoming queue, incoming UDP channel. So for example, if you're an exchange and you have like your matching engine, maybe you want to give your matching engine more priority over everything else because it's the most important piece of your distributed system. But by default, and that's on purpose, a node cannot flood the sequencer. Every node by default can only send like 32 messages to the sequencer, and then after that it's going to have to wait and pace yourself. So that's very important. You can control that, you can configure that, and that's responsible for guaranteeing fairness to the system. I don't think I showed this on the demo, but that's a fully deterministic sequencer clock. So basically the gateway was executing orders and it was providing like a timestamp for the execution. What happens now if you replay that file 2 years later? Is it going to timestamp with the current time, or are you going to use the time that you used like 2 years before? No, it's going to use the time you used 2 years before. Again, this is completely deterministic. Same input, same output. So it uses the time that's flowing on the event stream. The event stream has so many messages, and you can also have heartbeats there, that it can kind of like make a global clock tick. So the tick of the clock is in the event stream. That means if you execute the same code 100 times, no matter when, the timestamp that the code is going to calculate is going to be the same. And that also allows you to have deterministic timers. If you want to set like a timer to cancel order like 10 nanoseconds or 10 microseconds later, if it doesn't get filled, you can do that. It's gonna happen, it's gonna be triggered by the event stream, and 2 years from now when you execute the same code again, it's gonna trigger again because it's deterministic. Last but not least is a very advanced and very useful feature, which is the ability to run multiple sequences in parallel on completely independent multicast channels. For example, if you want to run market data and orders on the same sequencer, that's probably not a good strategy because market data is very high in volume, and you don't want your orders like having to compete with market data message to be executed. So what some people will do is they will have two sequences, one for market data and one for the order messages. Those two sequences are completely independent. They run in parallel on separate multicast channels. And what you can do is have some cross-connect nodes, which are nodes that are connected to both sequences and can send like some message from sequence A to sequence B and vice versa. For example, if you have a market data sequencer, you don't want to have all the incremental message on the order routing sequencer, but every second you might want to send a top of book on the order routing sequencer, just for reference, just so you know how the market looked when you're placing orders and whatnot. So now let's talk about the sequence highlights to kind of wrap up. So what are the sequencer and what is it good at? It's great in implementing ultra-low latency distributed systems with a lot of moving parts, which need real-time monitoring and real-time reaction capabilities. We're talking about exchanges, trading platform, banking systems, credit card systems, payment systems. They need real-time reaction capabilities. The sequence allows nodes to truly run in parallel, meaning like you have true parallelism here. You can run two separate nodes on two separate CPU cores, even in two separate machines. I mean, they really run in parallel. All nodes see the same message in the same order. I mean, that was repeated like 1,000 times. That allows for tight integration across the whole distributed system, meaning like there's no inconsistencies across nodes because they always see the same thing. Nodes can evolve independently, and that's the biggest advantage of the sequence platform, meaning like you can add more nodes and code more nodes and change nodes without affecting other nodes. They are completely decoupled, and you can evolve them independently. One node doesn't affect the other node, doesn't affect the distributed system. You can create a node that's buggy and slow. I mean, it's your node problem. It's not going to affect the other parts of the system. So that's pretty useful. So when a node fails, another node can be running and building state to take over immediately. So fault tolerance and high availability, it's given for free by this architecture. Because of the determinism, clusters become like a natural thing that you can code, because you can just run two nodes in parallel. They're going to see the same message. They're going to be the same state. Everything is deterministic. They can become a cluster. You can have a hot, a hot, warm, active, active, or active, passive, failover. So that becomes trivial. Nodes can lag during activity peaks without affecting the distributed system. That's also, you can have a very slow node that is inserted into a database. It's going to lag behind. He's going to have to request replays from the replayer. Maybe it's connected to a bridge, so it doesn't like even affect replayers. It only affects the bridge it's connected to. But yeah, it's very easy to have elasticity in this kind of system, meaning like when you have peaks of load, that's fine. Some nodes are going to lag, but the system as a whole is going to continue to operate. Nodes can fail. They can stop or be taken down for maintenance without affecting the distributed system. Like I showed in my demo, you can bring a node down, bring a node up whenever you want. The state's going to be rebuilt. Everything works. Just add more nodes to grow and scale. You have horizontal scalability, load balance. This is given for free. You want to scale your system, just add more nodes. You want to have 10 gateways instead of 2, just add 10 more gateways, and that's it. So you have unlimited possibilities with this kind of architecture. And now to really wrap up, let's answer some frequently asked questions that someone not familiar with the sequence architecture would normally ask. The first one is like, come on, my node only needs a few messages from the event stream. Why does it have to receive all the message? Well, because that's the main paradigm of this system. That's what creates determinism, consistency, clusters, high availability. So yeah, there's always a trade-off for everything, but usually that's not a problem at all because the system is very, very, very fast. Remember, like, can send like 500,000 messages per second, even 1,000,000 messages per second if you're having like, if you're able to batch because your messages are small. So this is not a problem most of the time, and that gives you so many benefits that that's how it's being done, and that's how people are gonna continue to do it for the benefits it offers. So that's a very good question. Failover for the sequencer is just for hardware failures. Remember, a cluster is going to be running the same code. So if you have like a software bug in one instance, the other instance will also have the same software bug because it's the exact same code executing on top of the exact same input. So failover will not get you away from software bugs. Failover there is for hardware malfunctions. And that can happen, but that doesn't happen often. I mean, in 5 years, I saw it happen like twice, hard drive failure, things like that. So when that happens, you can fail over automatically. You detect like the sequence is not sending heartbeats or messages, but then you can have like the split brain scenario, which you put you in a lot of trouble. I know there's like some consensus algorithm that you can use to kind of like walk around that, but because but those consensus algorithms introduce a lot of complexity to the system and a lot of overhead. Remember, the latency is the main goal here, and like I said, if that happened every day, yeah, you're gonna have to have it like some kind of automatically consensus mechanism to fail over. But those kind of systems that use the sequencer, trading systems, exchanges, there's always like a human watching the system 24/7. You're not gonna have an exchange or a trading system like everybody's sleeping and the code is running, right? That can lead to disaster, of course. So what happens is when there is a problem with the sequence, a hardware problem, a human can make sure the sequence is really dead before activating a backup one. Because you don't want to have a situation where you have two active systems, two active sequences in the system sending messages. I mean, that would be very bad. So historically, this has been doing like manually. We do support an automatically way as well, but it's not on by default. We don't recommend it. That seldom happens when you have to fail over the sequencer. Again, only when there is like a hardware problem. So that's why historically most of the sequence implementations out there do not use automatically failover for the sequencer. They use manual failover. So last question is, what happens when you're in the cloud and you're using TCP and you have to send messages to a bunch of nodes connected through TCP? Aren't you gonna have to copy the same message for each and every node? Yes, and there's no way around this problem. That's called TCP fan out. TCP does not have broadcast or multicast, so that's a problem that's inherited from the TCP protocol, and there's nothing you can do about it. If you have 100 nodes connected to a TCP server, the TCP server is gonna have to send the same message 100 times. That also creates a fairness problem, because the first client that connects to the server is gonna be the first client that's gonna get the message. There's ways around it there. You can randomize the way you send the messages, so the first guy who connects to the server is not the first guy. They always get the message, but the problem is still there. That's a TCP fan out problem. There's no way to solve that. We have ways to mitigate that, and the way we mitigate that is by introducing layers. So let's say you have 100 nodes. Instead of connecting 100 nodes to the sequencer, you only connect 10 nodes to the sequencer, the 10 most important nodes, the nodes that require the lowest latency, etc. And then that's going to be your first layer. And then you put a bridge on this layer, and then you connect more nodes on a second layer. And then you put another bridge on the second layer, and then you connect even more nodes on a third layer. So that way you kind of like distribute the load through layers. So your first layer is the most important nodes, the second layer is not the so most important nodes. Because like I said, there's no way to solve that. TCP unfortunately does not have broadcast. If you want like an efficient way to send the same message to many clients, you gotta use multicast UDP for that. And let's hope that soon enough, most of the cloud providers are gonna somehow give us like good multicast support. And another way you can use to mitigate this problem is to have several TCP servers in parallel, each one running on its own CPU core. So the way that works is the sequence would write only once to a shared memory on its machine, and then a bunch of TCP servers running in parallel would pick up those messages from the shared memory and serve their TCP clients. So by doing that, you can effectively like parallelize somehow the serving of the message by having several TCP servers running in parallel. Again, that only mitigates the problem. The correct solution for this problem is of course multicast UDP, but that's how we can mitigate the TCP fan out problem. And that's it. That was a little longer than expected, but I think we covered the most important parts. If you have any questions, please reach out, and I'll see you on another video.